This is Geometry Chapter 9 Final Review. Chapter 9 is all about transformations, translations, reflections, rotations, dilations, isometries, all of these words about taking shapes and kind of moving them around, sliding around and changing their sizes. So we're going to start off with being able to identify an isometry. If you remember what the word isometry means, what that means is that something is mapped onto itself. So this, or like the size doesn't change. So an example of an isometry would be a translation. You just pick something up and you move it. A rotation, you just take something and spin it. Reflection, you flip it over a line. Things that are not isometries would be like a dilation. That makes something bigger or smaller. Okay, and so that's kind of what this chapter was about. So in the diagram, figure UVWX is mapped, so UVWX is mapped onto LMJK. They want us to name the image of this segment VW. So we might start by actually finding VW. That's right here. Now, there's a few ways you can go about this. You can kind of see, okay, how do I take this original shape here, that solid shape, and end up with that dash shape? And you'll be able to visualize moving it. You can kind of see it swings around like this and rotates. You're able to identify the segment that way. But another way that you can use to identify it is when they say that something maps onto, that's the same as saying UVWX goes to LMJK. And so you can actually use that statement as well, since they did say it maps onto. They lined up all the corresponding parts. So here I might see, oh, that VW either goes to JM or KL. And if I'm still not sure, I can double check it here. Well, VW right here, second letter and third letter goes to the second letter and third letter there. So you would say that VW is a segment. It maps onto, that's what the arrow means, segment MJ. So that was that first objective. After that, we started to talk about translation images, so taking things up and moving them. You might have some boxes on your paper on some of these. You might want to kind of line yours up with mine and fix those. I kind of pause the video here for a second and do that. Okay, so we're supposed to find the image of C under this translation. So we start by finding C, and what we're doing is we're going to take C and we're going to move it. Now if you remember, the x-axis is the horizontal axis right here, and the y-axis is the vertical axis. So if it says x plus 4, that's moving it the left or right. If it says y plus or minus, that's moving it the up and down. So positive 4 is moving in the right, and negative 4, or if it was x plus 4 means moving to the right, x minus 4 would be moving to the left. So plus 4 tells me I'm going to take this point C and move it 4 to the right. So I go over 1, 2, 3, 4. Y plus 2 tells me I'm moving it up because up is positive. So it goes up 1, 2. Now we're lucky, there's a point there. So we can say, well, C goes to B, or we could write the ordered pair of B, so we can count that out, start from the origin, goes over 2, up 1, 2, 3, 4. So you could either say B or the ordered pair 2, 4 that it maps onto. So the next thing is, how do we write a translation? Well, we kind of follow this rule right here of how they wrote. That's a translation rule. And so we're going to try and write the rule for translation from F to B. So we can kind of copy the outline of it. It goes X, Y, arrow, and it's going to go to some X and Y values. We're going to either add or subtract from X and Y. So we want to find that F. It's right here, and we want to go to that B right there, my green dots. So maybe I'll look at the horizontal change first. I'm going to the left. I went to the left 2, and when you move left, that's x moving towards the negative end, so that would be minus 2. So we would take 2 away from our x. And then to get up to the B, I add 4, increase that value by 4, so that means I'm adding 4. So that's a translation rule. All of those things together result in your translation rule. Here you've got some more boxes that were existing. All those boxes are either arrows or negative signs. So you might want to take a moment and pause and fix those on your paper. Okay, so what we are going to do is we're going to find the image of each figure under the given translation. So triangle ABC, it's missing triangle there as well, has this translation occur. So we're going to take all these points A, B, and C. Their original ordered pairs, negative 3, 4, negative 1, negative 2, and 1, 5. And we are going to translate them And when you translate them, if you remember, A doesn't go to A, it goes to what we call A prime. B will go to B prime, and C will go to C prime. That's what we call their image. You start with what we call the pre-image, and you end with the image. And what we're going to do is we're actually going to fill in these values in our ordered pair using the translation rule right here. So it says x minus 2. That means we subtract 2 from that x value, and well, negative 3 minus 2 is a negative 5. And then it says y plus 5, we take the y value 4, we add 5, 4 plus 5 gives us 9. And we have our first translation image. You pause the video and do the next two on your own. Alright, you can check your solutions with mine. I got negative 3, 3 for B prime and negative 1, 10 for C prime. So this next one, there's not a lot on it. It's being able to find reflection images of figures. It says each point is reflected across the line indicated. Find the coordinate of the image. So we're going to take this point A and reflect it across the x-axis. So I like to figure out, okay, here's A, and then I think about the axes. You might even see that the axes are labeled. Here's the y, and here's the x. So this would be our x-axis right here. We're going to take A and reflect it across it. So there's a few ways to do that. If you remember your rules, you could just follow the rules for how to reflect. If you don't remember your rules, there's a nice way to do it too. You can just count how far it is to the line of reflection. It's 2, and you go that far in the other direction. 2. And so this is where I'm going to end up. A would go to point D, which is at, or not point D, sorry, point C, which is at the ordered pair 2, negative 2. If you remember the rules for reflecting in the x-axis, the rule for that was that xy goes to, x value stays the same, but the y value is the opposite. That was our rule for reflecting in the x. Why don't you try and write your rule for reflecting in the y? Pause the video here and try to write the rule for reflecting in the y-axis. And our y-axis reflection is that the ordered pair goes to the opposite of x and y remains the same. If you got that one, good job. All right, so then after that, we started to talk about symmetry. This is how many lines of symmetry does each figure have? So what a line of symmetry does is it cuts a shape exactly in half and both halves are the same. So you might see like you've got the sun here and then some weird abstract thing. The sun has a line right there, right down the middle, so that's 1. Okay, and then, well, you might see there's another one across. Here's 2. And maybe another one here, 3 and 4. And you might stop right there, but if you stop right there, you're actually missing some lines. Let's see if you can try and find those other lines. So pause the video here, see if you can find where the other lines are. You can see that I found that there's also kind of these green lines in between, like in between these two triangles and those other two triangles. Right here, you create a line of reflection, and you can do that between all of them. So there was 4 red and 4 green for a total of 8 lines of symmetry. Now, another way to do this that we talked about is you can really take this shape. If I erase all these, if I connect the points of all these triangles and erase the sun, I create an octagon. And since it's an octagon, octagons have 8 sides. There's 8 lines of symmetry as well. Okay, so if you can model a shape with a polygon, you can with an equilateral polygon, you can actually also create or figure out your lines of symmetry that way. So if we look at this thing, some kids like to draw a line of symmetry here or here, but if you look, if I had drawn in this first line right here and tried to fold it up, this part is not going to line up with that part down there. And now if I try it the other way, if I go this way, this part and that part aren't going to line up. They're going to go actually opposite directions. This one actually does not have any lines of symmetry. It does, however, have rotational symmetry of 180 degrees. So I can spin it around this point, and I can spin it all the way around like that to get 180 degrees symmetry, but it does not have line symmetry. The other thing we talked about is being able to understand dilation images of figures. This is when our size changes. It says the darker shaded figure is a dilation image of the lighter shaded figure. So darker is the image, lighter is the pre-image. So we start in the lighter and we're going to the darker, going that way. Is the dilation an enlargement or a reduction? What is the scale factor? So if I'm going from the lighter to the darker, you can see it's going from bigger to smaller. That's not an enlargement then, so that's what we call a reduction. It's not getting any larger, it's getting smaller. So this scale factor, what we do with the scale factor is we actually compare lengths. So you can kind of see these corresponding sides. I can see that this side right here in the image corresponds to this side right there in the pre-image. And so what I want to do is I want to compare their lengths. Well, in the image, that's 1 unit. I can count that out. And in the pre-image, it's 3. So when you write your scale factor, you take your image length to your pre-image length. Well, in the image, that side is 1, and in the pre-image, it's 3. So my scale factor then is 1/3. You can also check out with these horizontal lines. I can count this one out. This is 6, and that's going to go here to 2. I go pre-image to image, 2 to 6. That should simplify to the exact same thing, 1/3. Okay? So a triangle has an area of 40 centimeters squared. Following a dilation, the new area of the triangle is 360 centimeters squared. What is the scale factor of the dilation? So we talked about this a little bit in chapter 9, and then again actually in chapter 11. So you have a triangle that's starting with an area of 40, okay, and then it's going to end up with having an area of 360. So remember, scale factor, it goes image to pre. So we're starting with the 40 and we're ending with the 360. So it should go 360 divided by that 40. And so what we want to do is we want to take that and simplify that. If we simplify that out, we get 9 to 1. Or you might just get 9. Leave it as a fraction though, because a scale factor should be written as a fraction. And this though, careful, a scale factor is also the ratio of the perimeters. Okay, but this right here is the ratio of the areas. So we have to go from areas to perimeters. Now you've seen this a few times this year, a to b, a squared to b squared, and a cubed to b cubed. That goes our scale factor, our surface area or area ratio, and then our volume ratio when we have three-dimensional objects. What we have right now is this one right here, and we need to go backwards. So we technically have a squared and b squared. So to go from a squared, 9, back to a, we actually have to take that ratio and take the square roots. We go back and we get 3, square root of 9 is 3, and square root of 1 is 1. That's now our scale factor. Okay. So we're going to do a similar thing down here. It says the image of a beetle is 5 times the beetle's actual size and has a length of 1.75 centimeters. How long is the image of the beetle? Well, if we think about our scale factor formula, scale factor is the image to the pre. So if something is 5 times bigger, that's your scale factor. So we can plug that in for our scale factor. And this image length, this is the image length right here, that 1.75 centimeters. It says the image of beetle is 5 times as big and has a length of 1.75. So that's what we're going to put up above right here, and we're going to put our actual length that we're looking for down there on the bottom. And we get this equation that now we just need to solve. So we don't like to have x in the bottom, so we're going to multiply both sides by x to get it out of there. We get 5x equals 1.75. Now I have to get the x all by itself, so I divide both sides by 5. We go 1.7 divided by 5, and we get our actual length of the beetle. Then we should end up with 0.35. Now don't forget a label. It's talking about the beetle in terms of centimeters, so we're going to continue with centimeters then. Okay, we're getting close to the end here. Last slide. It says students will be able to find composition of reflections, including glide reflections. So it says find the image of each letter for a reflection, first across line L and then across line M, is the resulting transformation a translation or a rotation. So what we're going to do is we're going to first reflect across this line L the best we can, and then across line M the best we can. So let's start with that, because that one might be a little bit easier. If you see how far away from the line it is, we want to go that far below the line here again. So this is how far above it is. That's about the same length below. That's where I'm going to start then. So I'm going to go X, and then I kind of want to follow that down, X. Okay, so it's not quite perfect, but it's pretty close. And then we're going to reflect it across line M again. So it's a little bit closer to line M than it was to line L. Looks something like that. And what they want to know is if I skip that middle picture, how do I go from the first all the way to the last? So remember that a translation is just picking something up and moving it. And rotation is taking something and spinning it around a point in the center. Okay, so I can think about just taking this up, and all I did was technically just slide it down. That's your translation. And notice that the lines you reflected in are parallel. When you reflect in parallel lines, you get a translation. Let's look at the next one. We're taking T, we're going to reflect it first across line L. Now what I do is I take my paper and I turn it so that this is straight up and down, and then it's a little bit easier to do the reflections because you can see that like the bottom of T is a little bit closer and the top of T is a little bit farther. So you want to go kind of straight across that line. Okay, T is going to be right down there, and then it kind of comes up at an angle like that. That's pretty close. And now I would take my paper and turn it again so that line M is a vertical line for me. So this blue line, I would turn it to be a vertical line. It's a little bit easier to do your flipping then. And I can see, okay, well here's about the bottom of T, and then it kind of slants down a little bit. And then I get the top. And so what they want to know is how do I get from here, from this original T, here, this original T all the way to this new T. Well, you can kind of see that it's reflecting around this angle. Okay, and so that's going to, it's not reflecting, it's turning kind of around this angle, it's rotating. Now, rotation occurs when, notice these two lines that we were reflecting across, when they intersect. So intersecting lines when you reflect across them, that's when you get a rotation. Parallel lines, when you reflect across, you get what we call a translation. Well, that's the end of the Chapter 12 notes. For geometry, or Chapter 9 notes for geometry to get you ready for the final.